Okay, so let's talk about how we give different enantiomers different names. And this is done by adding the prefix R or S to the beginning of the UPAC name of the enantiomer. So uh, R and S are just designated letters. And the way we determine if we have the R enantiomer or the S enantiomer, the good news is there's only two kinds of enantiomers, R or S. What we have to do is look at the substituents that are bound to the stereogenic carbon. Okay, so very simply, if you have four different atoms bound to the central carbon, as shown in this bottom example, you give priority to the highest atomic number atom, which of course is bromine, and in chlorines 2, fluorines 3, and hydrogens 4. Okay, so you number each of the atoms that surround the stereogenic center. Remember, stereogenic center has to have four different substituents attached to it. Okay, and we see that's clearly the case. 1, 2, 3, 4, all different around the carbon shown. Okay, now if we have a tie, let's say we have two carbons attached to the same carbon, okay, but those carbons themselves are different. Well, we still have four different groups attached to the central carbon. Look at the 2-butanol example, and you'll see that the carbon shown, it's attached to the hydrogen and the hydroxyl group. That carbon's got four different groups attached to it, but you can see it's two of those different groups contain carbons that are attached. So what do? Well, we have the higher priority group is going to be the carbon that's attached to the two hydrogens and another carbon. Okay, and the methyl group is not attached to another carbon. So that's going to be lower priority. So because you have a carbon with another carbon attached, that is another priority group attached to it, rather than just hydrogens, which are always going to be the lowest priority. We make our ethyl group a higher priority than the methyl group. Okay, so our oxygen is going to be labeled number 1. The ethyl carbon is going to be number 2, the methyl carbon 3, and the hydrogen is going to be labeled 4. Okay. How about isotopes? Well, you want to take the heaviest isotope, that is the one with the highest mass number, and assign it the higher, the order actually of decreasing mass number. So, so tritium would be 1, deuterium would be 2, hydrogen would be priority 3 if you had 3 of those attached to the same carbon. Okay, so tritium is the heaviest, if you will, and because it has the 2 neutrons, and then deuterium, then hydrogen. That's the priority for how to determine the priority for isotopes. Okay, so the one with the most neutrons is number 1. And so multiple bonds. Okay, so we think about multiple bonds as bound twice. What do we mean by that? Let's take a look at the carbonyl, the C double bond O group that's shown in the example. Okay, and the way we would think about that group is 1 carbon bound to 2 oxygens. Think about that. It kind of makes sense. We're just visualizing this. It's a carbon double bound to an oxygen. So the way we would think of that, if we had to compare it to another double bound carbon, is to count that oxygen twice because it's double bound. Okay, so we'll see more examples of this. It should be getting clearer when we do examples too. So let's see, multiple bonds. Again, if we have a carbon that's bound to another carbon by double bond, we count that second carbon twice. So if something's bound If you have a double bond, you just count the atom that's doing the binding to the atom we're trying to assign priority to. We can just count it twice. If there's a triple bond, guess what? We're going to count the carbon in question 3 times. Okay? All right, so let's take a look at this figure 5.6. And how are we going to assign priorities? Well, let's take a look at the starred carbon. And, you know, as we've seen before, we add stars to carbons that are stereogenic. And so it's starred for us. And we can clearly see that there are 4 different substituents bound to that carbon. So what you do is go out one atom, start out going out one atom in each direction from that carbon. And we see that the first atom is a bromine or a carbon or a chlorine or a hydrogen. And we count bromine as we have no ties, so because they're all totally different. And so bromine is going to be priority 1, right? And then chlorine priority 2. And carbon, priority 3. We don't count the iodine, only if iodine were itself bound to that central carbon. Okay? So remember, we're looking at the first atom attached to the stereogenic center. If there are ties, then we'll go out to the next atom. All right, but for now, you can clearly see, just looking at the 4 surrounding atoms directly attached to the stereogenic center, we can see how the priorities are numbered. Let's look at the middle example, where we have 4 carbons as the first atom attached to our stereogenic center. And so how do we prioritize? Well, that isopropyl group, that is the one with the 2 methyls attached to the CH on the bottom, is going to be number 1, because that carbon that the arrow is pointing to is attached to 2 other carbons. So you go one atom out from that carbon and you see there actually are 2 atoms attached to it. So none of the other carbons are attached to more than 1 carbon. Okay, so you have a methyl, a propyl, and a pentyl group. So pentyl, because it's got more atoms there, it's going to be priority 2. Then propyl will be 3, and methyl is the smallest, so it's going to be priority 4. You see that? Even though the isopropyl group has only 3 carbon atoms, it's got that branch, so that carbon that's attached to our stereogenic center, because it has 2 bonds to 2 carbons, it's going to be priority 1. Okay, all the other carbons have just 1 other carbon attached to them, except for number 4, which is only hydrogens. Okay, let's look at the next example. And what we have here is another stereogenic center. Oxygen, we again look first at the first atom attached to our stereogenic carbon. And you see we have an oxygen that's going to have a higher atomic number than carbon or hydrogen, right? Out of the other 3 atoms attached to our stereogenic center. So that's clearly number 1. And hydrogen, again, hydrogen's always going to be number 4, right? The only thing smaller than a hydrogen is going to be a lone pair of electrons. And you're not going to see that counted in prioritization for a while. So your hydrogen can typically always be labeled as 4, as the lowest priority. So we have an oxygen directly attached to our stereogenic center. That's the highest atomic number atom attached to our stereogenic center. The other 2 atoms attached to our stereogenic center are both carbons. So what we do is we look at the next atom attached, and they're both attached to oxygens. But the carboxylic acid, the COOH, that has a double bonded oxygen. In fact, it's connected to 3 oxygens. You count the one that's double bound to the carbon twice, and then there's a 3rd one. So because that's got 3 oxygens attached to the carbon, whereas the CH2OH group only has 1 oxygen attached to the carbon, the carboxylic acid group is the higher priority. Okay, so then you can go around again and label these 1, 2, 3, 4. Of course, 3 is going to have a higher priority than 4 because it is carbon rather than hydrogen that's attached. All right, I hope you're getting this. Again, this is something else that comes with practice, and the more examples you do, the more problems you do, this starts to become very, very clear. Okay, so how do we actually assign the labels R and S? Okay, so let me just say that this is critically important. We all have stereogenic centers. Every amino acid, well, not every, except I guess for glycine, have stereogenic carbons. So this is critically important in nature. And so we need to be able to label these stereogenic centers as R or S. And how do we do that? It's a simple rule. We assign our priorities just like we had been practicing. And you see the two enantiomers of 2-butanol, that is 2 non-superimposable mirror images. Again, make a molecular model of each and convince yourself that A and B are not the same compound. Okay? So we assign, as you can see, the hydroxyl group number 1, the ethyl group 2, the methyl 3, and the hydrogen 4. I hope by now you understand how we come about that labeling, okay, of priorities. Okay, so what you do is put the lowest priority in the back. Okay, and again, this is why you need molecular models, because to do this just on paper, especially at first, it's a little confusing. But if you have a molecular model, it's out there in space and you just turn it so your hydrogen's in the back. And then what you do is you have priorities 1, 2, and 3 facing you. And you look at 1, 2, 3. If that is a clockwise orientation, right? See that? It's a clockwise orientation as we have in enantiomer A. That's going to be labeled R. And again, you have to have group 4 in the back and count 1, 2, and 3 and see if you're going clockwise or counterclockwise. If you're going clockwise, you're R. Let's look at enantiomer B. We put our hydrogen in the back, and that brings 1, 2, and 3, priorities 1, 2, and 3, those atoms facing us. And we see that 1, 2, and 3, if we look at them, our eyes are going in a counterclockwise manner. The counterclockwise, when that happens, for groups 1, 2, and 3, we label that as the S enantiomer. Okay? All right, so again, clockwise is R, counterclockwise is S, counting 1, 2, and 3, and the direction that you go when you do that. Okay, and you put those in the IUPAC name of the molecule, that is the official name, and for the enantiomers of each, and you have 2R, 2-butanol. Why the 2? Because the stereogenic carbon is carbon 2. Okay, it's carbon 2 of the longest chain. Why is that carbon 2, not carbon 3? Because that contains a substituent. Okay, and so again, same thing for the other isomer. We call that 2S2-butanol. Okay, so hopefully that is straightforward. Again, you need to practice this, especially with molecular models. If you don't use molecular models, you have to go through this, and maybe that's okay for you. But if you do this procedure in conjunction with molecular models, it's so much harder to make a mistake. It's impossible, really impossible to make a mistake unless you've connected the atoms in the wrong way. Okay, so you can do this rotation, etc., and so on, but with the molecular models, this is trivial. And again, you can just follow this with the models, and the more you do the molecular models in conjunction with the textbook and these slides, the better you'll get at it, and you'll have less need for the models, although I still use them because I know that They enable me to do things more quickly and without error. Okay, so what happens when there are two stereogenic centers? Well, then we have something called a diastereomer. So not an enantiomer, but a diastereomer. The difference between an enantiomer and a diastereomer, one main difference is that we have more than one stereogenic center. Okay, enantiomers have just one stereogenic center. They're mirror image, non-superimposable isomers. Diastereomers are molecules. And one main definition of a diastereomer is a compound with more than one stereogenic center. Okay, when you have two stereogenic centers, things start to increase exponentially. That is, four different compounds, four different stereoisomers can be drawn from from a molecule that has just two stereogenic centers. Some are not going to be mirror images. Okay, so the formal definition of a diastereomer is a non-mirror image stereoisomer. All right, let's look at some examples, and let's take a look at 2,3-dibromopentane. Okay, so we can draw a couple of mirror images, at least to start. And again, you can see that the author here, or the slides, using molecular models and transposing them to drawings again. This is exactly what I want you all to be able to do. Okay, and based on the connectivities, you can see that these are two not superimposable mirror images. Okay, these are two different compounds. All right, and now you can see, right, if you can try to rotate these things and they don't align, etc., and so on. So again, by using models of each, this is trivial. You can just see right away that they're not the same. Okay, so because this pair of diastereomers, this particular pair, are non-superimposable mirror images, right? This pair of diastereomers are enantiomers because they actually are mirror images that don't superimpose. But again, not all diastereomers are going to be enantiomers. So remember, there are four possible stereoisomers because remember, we have two chiral centers. Okay, so just to recap really quickly, two chiral centers. You will have you can have a pair of enantiomers that are non-superimposable mirror images, but you're also going to have more stereoisomers that are not mirror images of these. So let's create another, and possibly two more compounds. And what we do is we notice that we've we've transposed the bromine and a hydrogen, and these are still isomers. They still have the same molecular formula, but they're stereoisomers. They differ in the orientation in space. Remember, stereoisomers differ in orientation in space, and so rather than differ in their connectivity. Okay, that's a different definition that you should know. But stereoisomers differ in the orientation of the atoms in space, not the atoms that they're connected to. So you can see that A, C, and D, all the atoms still have the same connectivity, but notice the bromines have different spatial orientations. Okay, so C and D, with models, again, there's a reason it says with models, you can see, are these mirror images? Yes, they are mirror images of each other, but neither of those is a mirror image of A. Okay, so C and D look like, if they're non-superimposable, right, and I think they are. If they are non-superimposable, or maybe they're not, we'll see. Then what? Well, let's take a look. The mirror image. So we create C, and then we create its mirror image, and we see, if you have your models, you're going to find that C and D are not identical. They're non-superimposable mirror images. So what happened is, with these two stereoisomers of dibromopentane, actually we get two pairs of stereoisomers. That is, two pairs of enantiomers. Okay? And so the relationship between A and B, enantiomers, the relationship between C and D, enantiomers. Diastereomers are diastereomer describes the relationship of A to C and D, and of B to C and D. Got that? So clearly A and C are not mirror images, so they're diastereomers. Okay, same for A and D, same for B and C, same for B and D. A and B enantiomers, C and D enantiomers. A is a diastereomer of C and D. B is a diastereomer of C and D. Again, so because they're non-mirror images. Okay? Okay, so just know the difference between an enantiomer and a diastereomer. They have to do with mirrors. Okay. Hopefully that's clear. Again, with practice, this stuff becomes pretty trivial. Let's say somebody asked you to find all the stereoisomers of 2,3-dibromobutane. Well, you can see stars at two of the stereogenic centers, the two stereogenic centers. So the maximum number of stereoisomers is going to be 4. Okay, it's 2 to the n equals 2 for two stereogenic centers. Okay, so maximum number of stereoisomers is 4. 2 pairs of enantiomers, and we have diastereomer relationships as well. Okay, so if we want to actually do this and look at all 4 structures, you can draw enantiomers. Okay, that is, draw mirror images, right? And then try to draw another mirror image. Okay, and what you see is these are C and D actually are superimposable. They're identical. So how would you know that? Well, you use molecular models. So there are 4 possible stereoisomers. We looked at all 4 possibilities, A, B, C, and D, and we found that a couple of those, C and D namely here, are actually identical. They're mirror images, but they're superimposable. So guess what? I think there's only 3. There's only 3 stereoisomers here. So the way you test this, and let's go back, is you draw mirror images, right, of a couple of a pair of stereoisomers, and you see if they're enantiomers, and they are. A and B are non-superimposable. They're not the same compounds, but they're mirror images. And then you switch the atoms on one of the 2 stereogenic centers. That creates a new compound C that is a diastereomer of A. Okay? And again, because A and C are not going to be mirror images. And then we draw the mirror image of C to see if it too has an enantiomer, just like A has B. And what we see is the mirror image of D is the same as C. So there's no enantiomer of C. We just have A, B, and C as our stereoisomers. Okay? And so the relationship between A and B is going to be an enantiomer. The relationship between A or B with C is going to be diastereomeric. All right? And and C does not have an enantiomer. It's got a mirror image that is superimposable. All right, I hope this is starting to make some sense. Let's go on to something else that's called a mesocompound. Let's take a look back first. I'm going to go back one. Look at C and D. The way that I can tell just by looking at these that they're mesocompounds is because if I took that mirror and sliced the molecule in half, in between the two stereogenic centers, I'd see that those two sides are identical. Let's take a look at exactly that. So we have a plane of symmetry right down the center of the molecule, right in between these stereogenic centers, two identical halves. We call these mesocompounds. And whenever you have a mesocompound, its mirror image is going to be identical to it. Okay? And you can try and draw that and draw its mirror, and you'll see it's the exact same compound. We call compounds with these kinds of planes of symmetry that bisect the molecule, bisect the two stereogenic centers, if you will, and you get identical reflection from both halves of the molecules. These are called mesocompounds. Okay, so we've learned the terms stereoisomer, enantiomer, diastereomer, and meso. Okay, it's just four new terms. Okay, mesocompound is achiral. Okay, so a mesocompound is, we don't even though it has stereogenic centers, it's not chiral, even though it contains what look like stereogenic centers. What are stereogenic centers? Actually, each of those carbons has 4 different substituents bound to it, each of those central carbons. Okay, but it's not chiral because there's a plane of symmetry. Okay. All right, let that sink in for a couple of seconds, and let's go on. And of course, just to recap, there are only 3 stereoisomers when one of the stereoisomers is a mesocompound. You can't reflect it and get another compound, so there's only 3 stereoisomers of 2,3-dibromobutane. Could you take another compound, an analog of dibromobutane, and go through this and draw all the possible stereoisomers and label them, label the relationships between all 3 or 4 of those as enantiomer, meso, diastereomeric, etc., and so on. Now, even though C is meso, it's still a diastereomer of A. Okay, see that? They're still diastereomers because they're stereoisomers that don't reflect. Okay, even though it's achiral. All right, so let's go on and summarize here. A and B are enantiomers, non-superposable mirror images. C is a mesocompound because it has a plane of symmetry right down the center. Okay, the left and right halves are the same. And A and B, the relationship of A and B to C is diastereomeric. Okay, 1 pair of enantiomers and 2 pairs of diastereomers for 2,3-dibromobutane. Okay. How about assigning R and S? Well, we have not changed the rules. We still want to put the lowest priority in the back, and we want to put, and then we want to look at the molecule with the lowest priority atom, which is going to be hydrogen as usual on carbons 2 and 3, and then we see if groups 1, 2, and 3, that is priorities 1, 2, and 3, are in a clockwise or counterclockwise orientation. And what you'll find, and you should do this, and again, it's very easy with models, is that C2 is S and C3 is R. And identical compounds, you can tell without doing the mirror and superimposability, well, they're going to have the same chirality that is the same RS designation at their stereogenic centers. That should be sort of obvious. Okay, and the enantiomers are going to have opposite RS designations. Diastereomers have the same. Now, don't memorize this. All right, just make sure that it makes sense. Okay. Okay, so RS and something else that's SR, provided those are two different stereogenic centers. They are going to have what, right? You want to think about all these different combinations. So again, the rules, this rules still apply. You, even with more than one chiral center, if you can make a mirror image and it's non-superimposable, then that and non-superimposable, then those two mirror images are enantiomers. And if you can make another stereoisomer that is not a mirror image and not superimposable, of course, then you're going to have a diastereomer. Okay, and the RS designations are simply figured in the same manner. And what you're going to find is that the RS designations change, they go along with that. Let's take a look at 1,3-dibromocyclopentane. So the maximum number of stereoisomers is 2 to the 2 because 2 to the second power, because we see the two stars, we have two stereogenic centers. I hope you can decipher that those are stereogenic centers. Okay. However, looks like we have a mirror plane until we draw in the stereo projections, that is the wedges and dashes. Okay, and what we can see is A and B are non-mirror images. They're isomers in cis and trans. And cis and trans relationships are typically going to be describing diastereomers. Okay, when you're talking about cis and trans isomers, typically those will be classified as diastereomers. Why? Because they're not going to be mirror images. Because you have the two substituents that is cis or trans, they're not going to be able to reflect each other. Okay, well, one pair is on the same side, the other pair is on opposite sides, so they'll never really be able to reflect each other. So those kinds of stereoisomers are going to be diastereomers. Okay. But what about cis dibromopentane? Well, there's only one isomer here that the mirror image there, we test this by drawing mirror images, and what we see is they're identical, they're superimposable. So the cis isomers, whether we drew the bromines coming towards us, that is with the wedges, or back with the dashes, they're going to be identical, the mirror images. Okay, so those are not enantiomers, clearly. So that's identical. And this is an achiral mesocompound, because you can see, you can draw a plane, a symmetry plane, straight down the center from top to bottom through A. And both the left and right halves of A, you can see, perfectly reflect each other. So guess what? A is meso and achiral. All right, let's look at the trans isomer. All right, the trans isomer, and what we can see is, unlike the cis isomer, the mirror image of the trans isomer, they are enantiomers. They're not superimposable. Amazing. So B and C are enantiomers. So in the case of the cis isomer, they're identical. The mirror images are identical. Cis dibromo cyclopentane, we have identical compounds, but the mirror image of the trans isomer, we get another one. We get an enantiomer. So that's kind of interesting, again, because B and C are non-superimposable mirror images. Because we have one stereoisomer as meso compound, we only have 3 total of the possible 4 1,3-dibromocyclopentane stereoisomers. Okay? All right. So let's summarize some terms. Okay? It's not that many, but you'll be using these terms so often in your careers that it becomes second nature. So isomers are different compounds, essentially with the same molecular formula. Constitutional isomers have atoms bound to different atoms. Think about that. So we move an H from a carbon over here we move that hydrogen to a different carbon, but you still have the same molecular formula. We've moved atoms around, but you still have the same formula. Those are constitutional isomers. Stereoisomers, we have not moved any atoms from one atom to another. We've not broken and made any bonds, if you will. Right? All the bonding is the same, but the 3D spatial orientation is different. You have a hydrogen in the front or a hydrogen in the back, right? And that is going to give rise to stereoisomers. And you can have enantiomers or diastereomers. Enantiomers are going to be non-superimposable mirror images. Diastereomers are non-mirror image, non-superimposable stereoisomers. Right, again, tons of examples will help you as we've begun in this lecture. Okay. How about the relationship between non-identical molecules? Do they have the same molecular formula? No. Okay, we're done. Don't have to worry about isomerism. But if they do have the same molecular formula, they are isomers. Then we have what kind are they? Are they named the same? You can look at the name if you have the name available, and if they're cis and trans, they're going to be diastereomers. And then if you have RNS relationships, you can then find out by your analysis of mirror images and superimposability to check if they're in fact going to be enantiomers or diastereomers. Now, if you're not talking about cis trans or R or S stereogenic labeled centers, then you're going to have constitutional isomers. Okay, so that's it for introduction to chirality and the nomenclature of chirality, RNS, and enantiomers, diastereomers, mesocompounds, etc., and so on. Very, very important stuff. We'll talk about the properties of these kinds of compounds in our next lecture.